Why do modern networks work the way they do? Why do we have MAC addresses? Why do we have IP addresses? And rather than just giving you the answer, sometimes you'll hear people say things like, well, an IP address is like a phone number and a MAC address is like a street address. And people will kind of, try to come up with these analogies to sort of explain these concepts. And what I've found is that a lot of times those concepts, those analogies don't really hold up. And sometimes they don't even make a lot of sense. So rather than just give you more analogies and try to kind of explain it in terms of, phone numbers or things like that, I want to give you a real quick and I think interesting history lesson about how networks came about. So let's go way back. Let's go back to the early days. And we're going to talk about, what is a network? What is the point of a network? Okay, so this is going to be a computer. Let's say we have a computer. We'll call it A. And just for the sake of this, we're going to go ahead and just say A is a MAC address and B is a MAC address. All right, we're going to kind of discuss what that means in a second. But the point of networks is an application running on one computer. So like A, let's say it's running some kind of, we'll keep it simple, a chat application, So you just type a message and it sends a message to another computer. So we've got A and B. And these two are running a chat application. And let's go ahead and add another computer here, C as well. So the point of networks is for an application on one machine to talk to an application on another machine, all right? So if A needs to send a message to B, it's going to create this little, what we call a frame. And this is going to have like a from and a to. So again, yes, I'm going to give you an analogy here, sort of like an envelope, from A to B. Okay, so now this is the way networks used to function. All these computers on the network would be connected to a single bus, okay? Bus, like BUS. It's called an electrical bus. And basically all that means is it's kind of like the electrical outlets in your house where the power comes in. And every outlet connected in your house, every outlet basically has power. It all kind of goes to the same line. So if you have, a lightning strike hits your main power line, guess what? It could go to all of those outlets. So it's the same concept here with this bus. So when A sends a message, it's going to put this out on the wire, and this message is going to go along the bus, and it's going to hit B, but it's also going to hit anything else that's connected to this network. So B is going to receive the message and C is going to receive it as well. Now B, obviously it knows its own MAC address and it's going to say, all right, this message is for me. And so it's going to process that frame. Whereas C, on the other hand, is just going to see it and it's going to ignore it. All right. Now, something that happens here that's kind of interesting is that anytime a message goes out onto the wire here, onto the bus, all the computers connected to the network, they have to stop what they're doing and they have to process it. Okay, they have to look at the frame and say, look, is this for me or is this not for me? So that's going to interrupt them. So the more computers you have on this network, the more interrupts you're going to have. Okay, so potentially there's the potential, at least, think back in the day when processors were very slow, it could basically add to the time it took the computer to do whatever it was currently working on. Another thing, too, about this is because this is a shared medium, so this is what we call a bus. Like I said, this is a bus, an electrical bus. It's a shared medium. All the computers share it. Now, one of the problems with shared media is that when one is talking, the others cannot talk, right? So if A sends a message out during that moment when it's sending that message, B and C, if they try to send a message, guess what? Those signals are going to interfere with each other, and it's going to be like just talking over each other. It's like two people trying to talk to each other at the same time. You're going to get this interference. These computers sort of have to wait their turn, and if you have a situation where both are trying to speak at once, well, again, their signals are going to collide, and then they're going to wait a random amount of time. And then one of them is, of course, going to send when the wire is silent. So that's going to slow things down tremendously, right? Because now it's basically one person or one computer at a time, right? So we call this a half duplex. All right, so because of these issues with shared media, we had to create something else. I'm going to erase this. We had to create this device called a bridge. So the way the bridge works is let's go and draw again A, B, and C. And then we're going to add a few more. We're going to add D and E here, okay? So these A, B, let's say A, B, and C are all connected to this one bus. And then D and E are connected to a separate electrical bus, okay? And we want to connect these two. We want A to be able to talk to E and D to be able to talk to C and all this good stuff. All right, let me fix my B. It's terrible looking B, okay? So this device called a bridge was invented. Bridge. And so what the bridge does is it is designed to essentially break up the electrical bus, the shared media, into what are called separate collision domains. Okay, it's called a collision domain because, like here, if A and B speak at the same time, it's going to cause a collision, right? Their signals are going to interfere with each other. So here's the way this works. Let's say that A wants to send a message to E. So it's going to form its little frame there from A to, I said E. Yeah, let's do E, okay? So what's going to happen is this is going to go out onto the wire, and it's going to go to B, and it's going to go to C, and they're going to say, these are not for me. They're just going to ignore them. The bridge is going to get this, and let's just say we're starting fresh, like we just set this up, we just turned everything on. We're all kind of starting from a blank slate here. The bridge is going to have two ports on it, okay? So it's going to have, we'll call these ports 1 and 2, okay? So port 1 is facing, or is connected to the bus with A, B, and C, and then port 2 is connected to the bus with D and E. So the bridge is going to, it's going to see this message from A, and it's going to say, well, that message is destined for E, but I don't know where E is. So what the bridge is going to do is it is going to do what's called a unicast flood. It is going to send that packet along its port number 2, which is connected to D and E, and that message is going to go to D, which of course is going to ignore it, and then E is going to receive it, okay? So at this point, because the bridge has received a message from A, it's going to start building this table. And you probably have heard this term. It's called a MAC address table. So the MAC address table is going to consist of a MAC address and a corresponding port. So it says, I saw this message from A come in on port 1. So now I know that A is connected to port 1. Okay, so this, again, this table is stored within the bridge. Now E, when E, responds, let's say E says, all right, I'm going to send something back to A, from E to A. I should probably make this a different color. All right, so let's say this goes back from, let's use blue. From E to A, so it's going to send this back on it's going to drop a message onto the wire here, and that's going to hit port number 2 on the bridge. Now the bridge is going to see this and say, okay, look, I've got this message from E that came in on port number 2, and there's the MAC address, all right? And the bridge is going to say, all right, look, I see that this message is destined for A, and I know where A is. It's on port 1. So it's, of course, going to send the message along, and that's going to hit C, and then it's going to hit B, and then finally it's going to hit A. And, of course, these other folks here, D, C, B, they're just going to ignore the message, but A is going to say, all right, that's for me. So this is how this bridge gets, this MAC address table gets built. This is how the bridge does it, right? So it's going to, when it's all said and done, the bridge is going to say, all right, B is on port 1, C is on port 1, and then what do we have left? D is on port 2, okay? So the bridge is going to kind of break up this collision domain here. We call it a collision domain, again, because when one machine on the shared medium is speaking, the other ones have to wait their turn before they can speak. Okay, so by doing this, we end up in a situation where potentially A and D could speak at the same time because they're not sharing the same electrical connection. Okay, they are separated by this bridge. So this is good, but we still have a couple problems with this. Is, of course, the more computers we add, the more bridges we have to add. And when the bridge doesn't know where a machine is, when it doesn't know which port a particular MAC address is connected to, it is going to have to do this unicast flooding. So essentially, we're still going to end up in this situation where signals get dropped onto the wire and you still have this half duplex communication where the machines cannot all communicate at the same time. So this is where we came up with a different idea. We said, let's change this up a little bit. Rather than having multiple bridges and these multiple like segments of the network, why don't we use the same concept as a bridge, but extend it a little bit? So rather than having this bridge with basically just like 2 or 3 or a few ports, what if we took this concept of the bridge we can just have a machine connected to each of these ports, right? And then we can just add, let's add E here. So we've got A, B, C, D, E, and then we'll go to F here, right? So now we've got all these ports, and we call this device a switch, okay? So what the switch gives us here is that any of these machines can speak, right? They can speak because they each have a dedicated electrical bus. They have a dedicated bus, a dedicated connection to the switch, and the switch is going to juggle all this traffic, right? So now let's say A wants to send a message to C. And again, starting from scratch, we started all this, we just booted everything. All this is clear. The switch has no idea who's connected to which port. So A sends out this message and from A to C, and the switch receives it, okay? So same as before, same as with the bridge, because remember, a switch is just a bridge. It is also going to build a MAC address table, okay? So it gets this message on its port 1 from A, and it says, okay, I know A is connected to port 1, and the message is for C, but I don't know where C is, okay? So the switch is going to, again, do this unicast flood. It is going to send the message out of all the ports except the one on which it received it, okay? So, of course, we're going to have this situation where everybody else says, that's not for me. This is for C. C's like, all right, that's mine. I'm going to process that. Everybody else kind of ignores it, right? So we still have this situation with the unicast flooding, unknown unicast, where if the switch doesn't know where a particular machine is located or which port it's connected to, it is going to have to just flood it and send it out to all the switches. But, when C responds back, we'll go with blue again. When C responds back to A, it sends it on port 3, and the switch sees that, and the switch says, okay, MAC address C is connected to port 3. And it says also, look, it's destined for A, and I know exactly where A is. It's on port 1. So now it's going to just send it out port 1. It's not going to flood it. So this does a couple things here. This gives us full duplex communication where all the machines can talk at the same time. The switch is going to handle all that for us. And as the switch learns where these machines are, it is going to avoid flooding as much as it can by only sending out the frames on the ports where it knows the destination machine is connected to. And another cool thing about this is these switches can be connected, right? We can add another switch. If we, run out of ports on the switch, might just be a really small switch. I'll give it a name like SW1. We could add another switch to it. Switch, we'll call it SW2. Let's say this is an 8-port switch, right? So we've got another port here, port 8, and we'll just connect this just to keep it simple. We'll connect it to port 8 on switch 2 as well. And then we'll have other ports. Obviously, we start at 1, and we've got computer G way over here. Starting to get a little messy, right? A, B, C, D, E, F, G, H, okay, connected to port 2, okay? And of course, this switch 1 has its MAC address table, but switch 2 is also going to have its own MAC address table as well, okay? So it's going to have, let's do it like this, MAC port. We're going to draw a little smaller now. And essentially, as traffic moves throughout the network, it's going to build a MAC address table that's going to look something like this. It's going to say, well, look, A, B, C, D, E, and F, those are all connected over here. These are all connected to switch 1. So anytime switch 2 sees traffic coming from any of these addresses, A through F inclusive, well, that traffic is going to have to come in on port 8. So it knows A, B, C, D, E, F. It says these are all connected to port 8. Okay, so they're all connected to port 8, and it knows that. And then, of course, G is connected to its port 1. Drawing my line, running out of space here. H is also connected to port 1. Okay, and likewise, switch 1, it's going to say, look, on port 8, I've got these MAC addresses H and G. So now we're getting closer to the way modern networks work. Now, we kind of further can break this down because, here we're dealing with physical switches. So if we want to add more machines, we add more switches. We still have the problem of the unicast flooding, where let's say switch 1 receives a frame destined for an unknown MAC address it doesn't know. It's going to flood that out of all of its ports. Let's go ahead and I'll do a green here. Let's say that E wants to send a message to Z, all right? So it sends this message to switch 1, and switch 1's like, I don't know where MAC address Z is. So it's going to do this flooding. It's just going to go flood it to all the ports everywhere, including to switch 2. And then switch 2 is going to say, I don't know where MAC address Z is, so it's going to flood it out of all of its ports, right? And so you can imagine a situation here where switch 2 is connected to switch 3, and that's connected to switch 4, and you could potentially have dozens of these things all kind of daisy-chained. Well, you end up with this flood. So now hundreds of machines could be getting flooded, and again, they're all going to have to stop what they're doing to process this traffic. Now, by the time we get to, the point in history where we're using switches, processors have gotten faster. It's not necessarily going to be noticeable. But, I do recall a time, and this was maybe 20 years ago, so ancient history by now, but there was one machine that was just sending out frames, broadcast frames nonstop. And it essentially took down an entire network, not just in one location, but actually 2 locations, because they were essentially connected sort of in this way, like we have switch 1 and switch 2 connected, but from a longer distance. So you still have this problem with flooding. When you get this flooding going on in the network, it could potentially cause problems. Look at this. This is really, really messy, okay? So how do we, if we want to just build like a global network out of this, we can't do it. Like, it's ridiculous. There's no way we can do this. All these MAC addresses, we would end up with a table, essentially like a global MAC address table that's probably millions and millions of rows, and it just wouldn't scale. It wouldn't work. So this is where IP comes in. So let's think of this in terms of building like a global network, or we call it an internet, where we've got, think of this sort of as like my network and your network. All right, so here's my network. Mine is going to be A, B, and C, and it's a pretty simple network. We're connected to switch 1, A, B, and C. All right, and there's port 1, 2, and 3. Okay, so this will be my network. And then down here, you're going to have your network. Okay, so here's switch 2. So this will be your network. And switch 1 and switch 2 are going to be connected. Again, we'll just do it on port 8. A, B, C, and then yours are going to be like D, E, and F. Okay. Now I just mentioned that using MAC addresses and that what we were just looking at there, it's not going to scale very well. All right, let me move this. 1, 2, and 3. It's simply not going to scale very well. Okay. your switch does not really need to know the MAC addresses of all mine, because potentially my network could grow or your network could grow, right? So now we would potentially have thousands or even millions of MAC addresses. So rather than addressing these machines by MAC addresses, which when you think about it, so far I've been talking about it like, oh, A has a MAC address, that's a machine, B has its own MAC address, C has its own MAC address. But when you think about it, the MAC addresses don't actually name the machine. So a MAC address names the interface, not the machine itself. Okay, so that's going to become a very important point here in a second. So what do we need? Well, we need a different type of device here. So let me erase this here. And rather than connecting switch 1 and switch 2 directly, we're going to go ahead, let me erase this correctly. We're going to go ahead and add a different device in here. And we all have heard of this thing. This is called a router. Okay. So the router is going to sit between my network and your network, and it's going to act as what's called a gateway. Okay, so a router or a gateway, kind of use those terms interchangeably. Now, the router, of course, notice it has two interfaces, right? So the router, let's say it's got ports, I'm going to kind of do it like this, 1 and 2, so tiny, got to write real tiny here. Port 1 is going to have a specific MAC address. It's going to have one MAC address, and then port 2 is going to have a different MAC address, okay? So connected to each of these networks, the router is going to have different MAC addresses that, so your switch 2 is going to see the MAC address of the router's port 2, and my switch 1 is going to see the MAC address of the router's port 1, okay? So again, I don't want to get into too many examples here because we'll get really deep into the weeds, just trying to kind of keep this high level. But the point is, your network and my network are not going to see each other's MAC addresses, okay? So now we need a different way to address our networks. And again, this is where IP addresses come in. So what we'll do is we'll say, all right, we'll just have an agreement and say, look, for my network, I'm going to use 192.168.0, I'll do 10.0/24, okay? So that'll be my network, and then yours is going to be 192.168. And we don't really expect our networks to get super huge, but again, once you get even into the hundreds in terms of machines connected to the same shared medium, the same Ethernet, you potentially could have some issues with the unicast flooding. So we're going to make your network 20.0/24, okay? So now what that means is we can address our machines accordingly. So 10.0, I'm starting with 10.0, and I'm going to just start my addressing at like 10.100. So A, I'm just going to do the last two octets. So it'll be 10.100, and then B is going to be 10.101, and C is going to be 10.102, okay? And then D, that's your network, 20.100, E is 20.101, and then F is 20.102. Now here's the thing, and this is where back when IP was new, there was a big debate about this. And the debate was, should IP addresses name the machine or should they name the interface? Okay, now remember what I wrote up here, MAC addresses name the interface. So we already have something that names the specific interface of the machine, but what is an IP address going to name? Is it going to name the interface or is it going to name the machine? Well, the decision was made that the IP address would also name the interface, okay? Now, some of you might be thinking, well, what about Anycast? Aren't there IP addresses that are assigned to multiple machines, multiple interfaces? And the answer is yes, but that doesn't change the fact that the IP address is assigned to the interface, okay? So you can maybe assign the same IP address to different machines. You're still assigning the address to the interface. So the IP names the interface as well. So that's why I kind of wrote it the way I did, where we have the IP address sort of attached there to the interface. So now the router, of course, is going to have its own little table here, the port, and it's going to have the MAC, okay? So the router is going to say like, okay, on port 1, I've got the MAC of, switch 1 here, and then, and of course that's going to be switch 1's port 8, and then 2, I've got the MAC of switch 2, okay? So the router has its own MAC address table, so it kind of keeps track of what's where. So it knows, all right, look, I know that this network 192.168.10.0/24, it corresponds with switch 1's MAC 192.168.20.0 corresponds to switch 2's MAC, okay? So what's cool about this now, notice, is that the router does not need to know the individual addresses of every machine. It doesn't need to know that E is 20.101, okay? All it needs to know is that this 20 network, 20.0/24 network, basically it's reachable via switch 2, okay? And it also knows, of course, that switch 2, based on its own MAC address table, it kind of knows that switch 1 is connected to port 1 and switch 2 is connected to port 2, right? So it knows the MAC address and it knows the port on which that MAC address is reachable. Okay, so now the router is able to sort of span these two networks. It's able to pass IP traffic between these two networks without having to know a lot of details of the inside of the network, right? So this makes things very nice and very scalable. All right, very good. When we have a static network here, I've got my network, you've got your network, we kind of have this agreement. Everything is very nice, very clean, very predictable, and it's scalable, right? We can add more machines as we need to. And in fact, within our own individual networks, like you within your network, if you want to add additional subnets, IP subnets, you can add your own routers, and you could sort of break up your network. This is called IP subnetting, where you basically take your little IP block here, your 20.0/24, and you can further break this down as you need to, right? So now we have this flexibility where we can add more machines to our networks, and we're not going to have this issue with excessive broadcast or excessive unknown unicast, because now we can just break up the networks using routers. So this is the way it was for a long time, and this worked really great until virtualization came along. And I'm talking specifically about machine virtualization or server virtualization. Organizations would have these data centers, and we can sort of let's sort of reframe this whole thing here and say, instead of my network and your network, let's just say we are one big happy organization. Let's say we've got our two different data centers. We've got a site, let's call this ATL, where I used to live, site Atlanta, and then we've got a site in boy, I don't want to use California. All right, well, how about what's a nice place? Who wants to live? Where would somebody want to live nowadays? Boy, it's really sad that I can't even think of like a place that people would actually want to live nowadays. All right, I'm going to go with Tennessee. Let's say Nashville. I'm not saying I want to live in Nashville, but I know some people in Nashville. All right, so we've got these two sites. And these both belong to the same organization, right? And we're running servers here, right? We got like this big operation going. Don't think of these now as like individual PCs. Think of these as servers. These are very important servers. Each one of these is very important. And something happens, Atlanta sometimes gets tornadoes. Let's say we have an issue now where we know there's some inclement weather coming, some problems are going to happen at the Atlanta site. And we say, listen, wouldn't it be awesome if we could take server A right here, and if we could just, in anticipation of something bad that's going to happen at the Atlanta site, if we could just move A to Nashville, sort of draw a little like dotted line here where these two are separated, right, by this router. So they're connected at a long distance via like private line or something. But we have these two sites connected. But so wouldn't it be cool if we could somehow move or migrate server A to this Nashville site? Man, wouldn't that be awesome? Well, the problem here is that server A has its own IP address in this 10.0/24 network. So it's got the address of 10.100. So now if we're going to move A from Atlanta to Nashville, well, what do we have to do? We have to change its IP address in order for this to work. Because remember, everything here, everything in the Nashville site is configured with this IP addressing scheme. So this concept of moving one IP address, and if we want to be technical, moving one interface from one subnet, one IP subnet to another, this is called IP mobility, okay? So essentially what we're doing is we're saying, look, I'm going to go ahead and erase this. A lives up here, and it's got a particular IP address, and it's got a particular MAC address, right? What we want to do, and remember, the IP address and the MAC address both name the interface. And what we're saying is, look, let's move A down here, change the IP, but don't change the MAC. Because of this decision that was made so long ago, IP address naming the interface, we have big problems with IP mobility. Now, if we want to like move one server from one site to another, essentially moving it from one Ethernet subnet to another, well, guess what? We've got a problem now. Okay, so this is where these other kluges were invented. You've probably heard of things like VXLAN. There's other technologies, but basically, this idea of routing layer 2, which is Ethernet, over layer 3, which is IP. But we have to basically move layer 2 over layer 3, and this creates all sorts of problems as well. So whenever you're dealing with networking and you're like, why is it so difficult? Why did they do it this way? Why do we have to do things this way? Why don't we do it a different way? You probably thought, man, I would have done it this way if it was up to me. Well, just remember, this is the reason. IP addresses name interfaces, they don't name the machine. And, again, I mentioned Anycast. We try to kind of get away with this. Like, well, why don't we just have another server down here that's sort of like mimics server A, and it has the same IP address. Why don't we just sort of duplicate this 192.168.10 network? Why don't we duplicate this down here and just run it like that? So again, there's all kinds of problems that come from this, but essentially that's the way that networks have progressed over the years. It's sort of been like, we do one thing and it works for a while, and then as we grow and add more machines and more people, we say, well, this isn't going to scale. We have to do something differently. So we sort of add layers on. We kind of add these kluges on as we go, and this has been happening, for decades now. So now here we are 40, 50, 60 years into this, really, and we're still using this same Ethernet technology for the most part. This idea of MAC addresses that was invented 50 years ago. Okay, so we're really using 50-year-old technology, and you always hear things like, well, that technology's, we don't use that anymore. That's ancient. That's outdated. And there are a lot of things that do just go away in the tech world, but Ethernet is not one of them. Ethernet has been around a long time, and we're still using it because it's something that sits at such a low layer, and everything else is built on top of it that it's foundational, and we can't really just rip it out and replace it. Same thing with IP. IP has been around for a good 40 plus years. A lot of things are built on it, so we can't just replace it. People tried, oh goodness, it's been 20 years now where IPv6 came out. And what a lot of people don't realize is, let's erase this. IPv6 is not a new version of IPv4. So people had this idea, wouldn't it be great? Remember the issue with IP mobility. There's another issue too with IPv4 where there's a limited number of addresses because of the address space it's basically 4 octets. So if you were to do up to 255 for each octet, you've got a limited number of addresses here. So this idea was in the early days of the internet, everybody could get a public IP. I mean, there are companies that would we want a class A, which is a huge number of addresses that never get used. So we kind of ran out of allocations of IPv4 addresses. So IPv6 came along, and you get enough addresses for, if you have an ant farm, every ant in your ant farm could have its own internet. It's a huge number. So people thought, oh man, if we could just replace IPv4 with IPv6, that would solve a lot of our problems. Of course, the problem is everything is built everything is built on IPv4. It's foundational. And IPv6 is not like, people think, oh, it's a new version. And you think like, oh, I'm going to upgrade, my operating system. So you just like install it or something. And it's not, it doesn't work like that. Like it's totally different. Everything's built on IPv4. It requires not really replacing it, but simply building a new protocol. Of course, IPv6 is relatively new. It's a totally new protocol. It's not a new version of IP. It's literally a totally separate protocol that behaves differently, functions differently. So we're going to have to sort of build this new IPv6 protocol alongside IPv4, and as best we can, migrate things over to it. Well, IPv6 is out there, it is used. It is nowhere near replacing IPv4. And remember, IPv6 has been in play for 20 years now. People have been actively trying to push it. It is nowhere near replacing IPv4, and I don't think it ever will, to be honest. The only thing IPv6 gives you is more addresses. That's it. There's really no other practical benefit other than a larger address space. All right, so let's talk about the practical tips here I'm going to give you from all that. So that was fun. I think learning theory and learning history is always, it's a lot of fun. It's interesting. It's a good feeling when you can like look at something and say, I know why that works the way it works, right? But let me give you some practical tips. When it comes to designing networks, you want to have basically small broadcast domains. And what that means is very simple. Small broadcast domains means as many routers as needed. Okay, so what do I mean by that? Well, when I say small broadcast domains, I just mean avoid having everything on the same Ethernet segment. If you've got, say, something like this, where you've got a /16, okay? This is probably a bad idea, okay? Because now you have hundreds of devices essentially in the same subnet, huge broadcast domain. And remember, what was the problems with a huge broadcast domain? A lot of interrupts. And then there's potential for basically network outages. If you get a NIC that goes crazy and it just starts flooding, right? You get these broadcast floods. That can cause issues. You want to subnet as much as you can, really, as much as you need to. And again, what that looks like, there's no like hard and fast number, but as a general rule, I would say keep it to like less than 100 devices per subnet. So rather than doing like a /16, I would probably do something like, let's see, maybe even something like a 28. Like I would try to keep it pretty small here. So that way you're limiting the broadcast domain. You're sort of limiting the blast radius if something bad happens here on your network. Try to keep these broadcast domains small. Having said all that, I know some of you, if you've worked with cloud, you might have some objections and say like, well, wait a minute, how do the cloud providers do this? The cloud providers have a really neat trick. Cloud provider trick. Okay. So the trick that they do is they eliminate broadcasts. That was the problem from the beginning. Remember that with Ethernet? We have one machine talks and all the other machines have to listen, right? And even with switches and everything else in play, we still have the problem of unknown unicast flooding, okay? So this was an issue early on. The cloud providers were like, this is going to be a scaling issue. How do we solve the problem? Well, obviously somebody pretty smart said, the problem is broadcasts. So why don't we just block those? Why don't we just eliminate broadcasts? Let's sort of break Ethernet in order to make scaling work better. So if you have, like, say, I'm an Amazon guy. So let's say you've got a VPC and you've got an instance, EC2 instance, with a certain IP address, and they're going to be in the same VPC, same subnet. We're just going to stick with the 10. 10.101, and then instance 2, 10.102. I could probably diagram this too. If instance 1, let's say you pop a shell on there, it's just a Linux machine, and you say, all right, ping-b, and you ping the broadcast address. You know what's going to happen? Instance 2 is not going to respond. In fact, it's not even going to receive it because the cloud provider is going to block that broadcast, right? Now, you try the same thing on a regular network, you're going to get a response, right? All things being equal here. So, but the cloud providers, by simply breaking broadcast, eliminating broadcast, they have solved the scaling problem. Now, in doing so, they have also broken some other technologies. There was an old thing called the Microsoft Network Load Balancer that actually depended on broadcast. And when I say broadcast, broadcast is a subset of what's called multicast. And Microsoft Network Load Balancer depended on, depending on how you configured it, multicast, broadcast. So certain things that depended upon the broadcast functionality of Ethernet did break and will not work on cloud providers. But you know what? That's okay, because what do the cloud providers give us? They say, listen, we're taking away broadcast. We're taking away some of people's toys here, specifically load balancers. We're going to have to, give that back in a different way. So, of course, they came up with like elastic load balancers of various types, layer 7 proxies, network layer 4 proxies. So they gave it back to us. They gave us what we needed, and they did it in a way I think that's much more scalable, right? So the cloud providers, I'll say the advent of cloud really did help a lot. And it's great because now, you can even sort of run your own private cloud. You've got things like Cisco ACI that sort of try to do some of the same things here. So again, modern networks are kluges built upon kluges, right? We've just got these layers of tricks and hacks that we've done just to make it work. So I'm not going to say it's quite a house of cards, but it is pretty delicate, probably not the most efficient, but you know what? It works. It works, and that's basically all we really care about. But now you know how it works and why it works the way it does.